Hello everyone. In this video, we will continue to examine topic 9.5, the Doppler effect, and in particular, we will begin to examine the case of a moving observer. Alright, so although the situations seem like they should be identical, as it turns out, there are differences between a moving observer and a stationary source, and a moving source and stationary observer. And what we have examined thus far is all related to this idea that you have a moving source and then a stationary observer, and then what is detected differs because the effective wavelength of what is being detected is either shorter in the case of an observer where the source is moving towards them, or longer in the case of an observer where the source is moving away from them. As you'll see, we will have to modify this analysis for the case of a moving observer and a stationary source, even though in our everyday experience, these are very similar effects. So if you have, if you're in a car and you're detecting a sound and you move towards that sound, you will hear a higher pitch, and then as you move past it, you will hear a lower pitch. But we will discover that the analysis won't be identical. Why? Well, consider. Again, how does the observed frequency f prime depend on the velocity of the observer, not the source now, and the emitted frequency? Well, think about that observer moving towards the source. So the observer is at A, for example, moving towards the source with a velocity u sub O, O for observer. Notice they detect the same wavelength that they would otherwise. This distance is the same for them. It's not any shorter than it was before. Okay, that distance right there, that lambda, is exactly the same. Okay, but what is different for the observer is that the observer measures a different velocity of the wave because they themselves are moving too. So they measure a different velocity. We'll explore the ramifications of this in a second, but I want to compare it to the previous case. In the previous case, they had a changed wavelength, so an altered wavelength, depending on whether they were moving towards or moving away. But the velocity of that wave detected, as you can see in this calculation here, is measured to be the same. So if you're an observer over here and you're detecting these wavefronts as they come in, you still measure those wavefronts as sort of hitting you at the same velocity that they would if those wavefronts had been emitted from a stationary source. This is not the case for the moving observer and the stationary source, where that distance stays the same, but from the perspective of this moving source, as they move towards these wavefronts, those wavefronts hit them faster, or more often, maybe is a way to think about it, than they would if that observer were not moving. And so although the wavelength stays the same, that measured velocity changes. And in particular, that measured velocity is v prime equals v plus u sub O, the velocity of the observer. This is a lot like if you had a child on a wagon, and the wagon was moving at 5 meters per second, and the child can throw an apple at, say, 6 meters per second. If that child throws the apple off the moving wagon, that apple will go 11 meters per second, as long as they're in the same direction. This is the same kind of transformation. This is known as a Galilean transformation for velocities. So we put these two facts together, v prime equals v plus u0, and our new lambda equals v over f, and we find that f prime, our new f, is simply the detected sort of frequency here. I'm sorry, our f prime is simply the detected or measured velocity divided by that same wavelength as before. And what you can do is combine this. So once you have v plus u0 divided by lambda, you can note that lambda, just as before, is also equal to f over v. As a result, the detected frequency is simply the old frequency adjusted by the velocity, v plus u0 divided by v. This formula looks very, very similar to the other one, but you'll notice that all of the action is in the numerator rather than the denominator. Don't worry, though. The IB will give you this formula. Just as in the previous case, for a moving observer and stationary source where the observer is moving away from the source, the difference between the moving towards and moving away from cases is just a matter of a minus sign. So without going through the full analysis again, notice that if you're moving away here, you're going to detect that the velocity of the wave that you are detecting is slower than you would expect otherwise, because you're sort of receding away from it. Okay, the same way that someone who is catching a ball might sort of pull away from the ball in order to reduce that effective velocity. So lambda prime equals lambda, just as before, but that measured velocity, v prime, is v prime equals the emitted velocity, the wave velocity, minus the observer velocity. You pull the same algebraic trick with lambda equal to v over f, and therefore f prime is equal to v minus u0 divided by lambda, and therefore f prime is equal to v minus u0 divided by v times f. As a result, that differs from the previous formula just by that minus sign. And so you can summarize these equations like so, where f prime is equal to v minus or plus u0 divided by v times f. Notice a hint that you need to be careful with your minus and plus signs is that they are reversed here. This is to keep the convention consistent. So notice that in our previous case, let's scoot back here, plus is away and minus is towards. In this case, plus is towards and minus is away. So this can get quite confusing. My strong recommendation, just as before, is to consider, in the case that you're being asked about, should the frequency be getting higher or be getting lower? If it should be getting higher, you choose the appropriate minus sign. If that frequency gets higher, you're going to choose the plus. If that frequency gets lower, you're going to choose the minus. And that's all there is to it. I would strongly recommend taking this opportunity before you move on to work through all of the embedded example problems in these notes with those solutions. There are several of them, and in particular, pay close attention to the graph shown at the bottom of example 9.19.